Hello, my name is David Olale, and today I'll be presenting my talk on explanatory machine learning model plots for epidemiological and real-world evidence studies. My outline, it's first I'm going to talk or give you a brief explanation about why I designed the PFAC macro program for checking the validity of machine learning model predictions. Then I'll talk briefly about machine learning models and the existing interpretability tools that can be used to explain model predictions. And then I'll spend a lot of time talking about this new tool that can be used to augment the existing interpretability tools for investigating model predictions from machine learning models, and then give you some takeaways and where to get the code that I present during this presentation. Machine learning algorithms are now widely used in real-world clinical settings, and they are used for a variety of clinical outcomes, such as readmissions, healthcare resource utilizations, treatment pathways, and medication adherence. Traditionally, for most real-world evidence studies, statisticians and scientists have often relied on classical statistical models such as logistic, regressions, decision trees to estimate model features and for performing causal inference analysis. On the other hand, machine learning algorithms such as gradient boosting random forest are underutilized in real-world evidence studies. This is partly due to the interpretability of these models, hence they are nicknamed black box models. In the pharmaceutical and healthcare settings, model interpretability is very crucial. Regulators, clinicians, they want to ascertain that machine learning model results are accurate, reliable, and they are free of bias. Now, let's talk about the machine learning models that are used to generate predictions. They can be categorized into two: the black box models, which consist of random forest, gradient boosting, and they're very good for big data analytics. They tend to generate highly accurate predictions. They are good for detecting nonlinear relationships and complicated interactions among model features. One constraint is that they are very hard to interpret due to a large number of parameters in these models and the association layers embedded in the algorithms. White box models, on the other hand, that include logistic regression, survival analysis, they are easy to understand and easy to interpret the features in these models. They often contain fewer model parameters and they can handle multi-level nonlinear data structures. They are often the preferred choice of statistical methods when it comes to hypothesis testing and causal inference analysis. So now look briefly at the interpretability tools that we currently use to explain predictions from black box models. The first one is variable importance ranking, and it's often used to discover features that are ranked as best candidates to include in a model. Then we also have partial dependence, individual conditional expectation, line plots. These allow you to go deeper and gain deeper insight of the inner workings of black box models. They can be used to examine the impact that different model features exert on model predictions. And we can also use them to do what-if scenario analysis, impact on one or more variables on the target variable. The PFAC plots that is the central thrust of this presentation are useful, and they augment the existing interpretability tools. They are good for checking posterior predictive distribution of model predictions, and they can also be used to check for consistency and sensitivity of the model with data. Why is model interpretability important? Because our ability to interpret black box is important for trust, transparency, and fairness. If we look at these two plots, what we see are the effect of age on probability of 30-day readmission, modeled by forestry and gradient boost. And the pattern of association represented by these two plots looks similar. But when we look at the effect at different age groups, we see some differences. And that's important because once a champion model is selected, we need to be able to ascertain that the model features that we're going to be using to explain the predictions are free of bias and they cannot give us unintended results. And that's why evidence generation becomes important. Attributes of good model should demonstrate reliability. And by reliability, it means reports produced by a machine learning model should be independent of the modeling method used. As data scientists, we should expect to see identical results from multiple algorithms that perform similar analysis on the same data when applied to the same question. The same thing is true for replicability. The ability to replicate and reproduce results from a machine learning model in different databases. For example, in real-world evidence generated from one analysis, I should be able to replicate that in another database that is looking at the same question. The next one is generalizability. This points to the value of being able to generalize model results beyond the modeling training database that produced the results. One thing that makes a data scientist happy is when identical analyses are performed against different databases and the models show consistent, similar results across these databases. And hence the need for a tool that will allow you to gain some deeper understanding of the predictions generated by these models. So now I'd like to talk more on the post-prediction model features association check macro that I wrote. What does it do? First, it allows you to obtain posterior predictive distribution of the model predictions on the training data. Two, one can generate plots that can be used to perform sensitivity and discrepancy test check of observed test statistics and discover replicate samples of the data. The tool can also be used to perform post-prediction check of the association between model input variables and the predictions, and is capable of detecting nonlinear association of feature interactions of the replicate sample of the data. These are some examples of the plots that can be generated using this macro program. And I'm going to go through each one with a use case that we describe during the presentation. First, let me talk briefly about the use case. Here, we are going to predict a 30-day hospital readmission using Model Studio pipeline and also using the PFAC macro to generate plots to explain the predictions from this model. The data that I'm using comes from the UCR machine learning, and I explain this in the paper. SAS Model Studio Pipeline can be used to build model and also generate interpretation of the model features. Here, I have built 5 different machine learning models. 3 of them are black box models, and 2 of them are white box models. The champion model selected after running the pipeline was the forest tree. And from the forest tree, we are able to generate important features, and important features are listed on the slide. Now that we see the important features, one of the other things that we can do really is to use the partial dependence plot to look at the relationship between features that is highly ranked and the probability of 30-day readmission. Here we've seen 3 different models fitted. And what is noticeable about this is that we see an increase in the risk of readmission as number of inpatient visits increases. What is also discernible is that each of these algorithms present a different picture of the relationship between this model feature, number of inpatient visits, and 30-day readmission risk. So how do we explain why we are seeing contrasting picture of model predictions looking at the same question? Here is where the importance of the PFAC macro comes into play. As I mentioned before, it can be used to generate posterior distribution of model predictions in the training database, and we can compare that to the predictions generated from the replicates of the sample, and I'm going to explain that. So the step for computing this macro is listed. First, there is a need to create the random replicate sample of the observed data, and this can be done using data step or use proc HP sample to generate the replicate sample. The other choice is the next step is to create a partition variable, especially if there's a need to validate the results generated from a training sample. We can use proc partition to do that. And another optional step is creating, using the proc binning to bin high cardinality variables or interval level variables into variables with smaller categories if we need to use them as plot variables. The next step is to now fit a machine learning model of choice. It can be one, it can be multiple. And once that is done, the results from these algorithms can then be passed into the PFAC macro. And the first thing the PFAC macro does is to create the replicate samples of the training data or the validation data or the test data, and then generate plots that can be used to explain the relationship between the features and the model predictions, or to also assess the model fit of the champion model. Now I'm going to go through the different plots that can be generated using the PFAC macro program. The first one is the model-agnostic posterior predictive distribution check of the predictions generated by black model and the observed data. The other set of plots that can be generated allow you to look at the sensitivity and to perform sensitivity and discrepancy test check of the test statistics generated from the training sample in comparison with the same set of statistics generated from the scored replicate samples of the training data. And we can do this to compare multiple machine learning models to decide which one we want to use in the real world. The next set of plots that can be generated allow you to look at the association between the model input variables and the predictions themselves. Maybe it can help us to really understand the nature of the association between the feature itself and the target variable. And last but not the least is that they are capable of detecting nonlinear association or feature interactions, which can help us to really improve the model in case these are not captured in the training sample used to select the champion model. So the first set of plots, like I mentioned, are called, and as you can see, this is a summary plot that checks the posterior distribution of the model predictions. Here we have used a gradient boosting model to generate an histogram based on the training sample and also based on the replicate samples generated from the observed data. The test statistics and the p-value suggest that there is no apparent discrepancy or deviation of the model fit of the training data when compared to the model fit of each replicate sample. The next set of plot that the macro allows you to compute is to perform a model comparison and assessment check. The plot on the left displays the model prediction from a random forest, and the plot on the right displays the model prediction from a gradient boosting model. We can notice that the effect of this variable on readmission risk is dependent on blood glucose status, which is our model feature that we are testing here. And we can see that the distribution looks similar across the two set of model predictions from the two algorithms used to fit the 30-day hospital readmission risk. The next set of plot that the PFAC macro allow you to generate, I call them the model feature assessment check plots. In this case, we can use the plot to examine the functional relationship between the model input and the model predictions. The plot displayed represent the check of the blood glucose test measurement based on the training data, and the right plot show model predictions based on the replicate samples also generated from the training data. We can notice that the effect of this variable on readmission risk is dependent on the blood glucose test measurement. The observed association between this variable, blood glucose, and readmission at the observed data level is also found in more than 2/3 of the replicate sample, suggesting a good fit of the model to the training data. Also, we can use the tool to check for nonlinear association and feature interaction. The example plots of age group and blood glucose are shown on this slide. The left plot presents the feature association check of age group on readmission risk controlling for the blood glucose variable. The same feature association check is performed for the replicate samples, and this is shown on the right plot. The plot shows a quantitative type interaction between blood glucose measurement and age group in relation to probability of 30-day readmission. And we can see that at the replicate sample level, there is evidence that suggests interaction of age group with blood glucose test variable, even though it's not clear-cut. There are other type of plots that can be used, that can be generated using this macro program. Here, I'm showing the relationship between diabetes medication and blood glucose test variable. And as you can see, the plots show a qualitative type interaction between blood glucose measurement and diabetes medication with regards to probability of 30-day hospital readmission. What is noticeable is a greater risk of readmission observed among patients with no blood glucose test measurement when compared with those that had blood glucose test measurements. And at the replicate samples level, we also see the evidence of interaction of diabetes medication with the blood glucose test variable. And we see that at each unique level of the blood glucose test variable. There are additional plots that one can generate. Here is the same one looking at number of diagnoses and blood glucose measurement variable. And the information that is important here is that we see that the more diagnoses recorded for a patient, the greater the risk of readmission, which may suggest evidence that sicker patients are responsible for the disproportionate share of observed readmission events. And the picture on the right, based on the replicate samples, demonstrate what is observed using the entire sample to examine the relationship between number of diagnoses and probability of readmission. We can also look at how length of stay affect probability of readmissions. So again, here we are controlling for blood glucose, and we also see a linear positive trend. As length of stay increases, so is the probability of readmission increases. And we see that difference among the unique levels of the blood glucose test variable. And one interpretation might be that those that are really sick, they tend to spend more time in the hospital because they have been taken care of compared to those patients that have less, that sickness status is less severe. So what are the takeaways? I've gone through the different interpretability tools that can be used to explain predictions generated from machine learning algorithms, whether it's a black box model or it's a white box model. These tools allow you to explain predictions and also to examine the functional relationship between model inputs and output predictions. The PFAC macro plots that I also showed and talked about during this presentation allow you to carry that further, in that they allow you to check for consistency and reproducibility of machine learning model results. They help to reveal input variable dependency and interactions, and they can also help reveal how changes in input variables can influence model predictions in different population samples. There is a limitation, however. The PFAC macro plots are not meant to be used for hypothesis testing, and also they cannot be used to reject or accept the validity of a model fit. The code that I used in this presentation, they are published in the conference paper, and also I'm going to make them available on GitHub. Thank you for your time.